All right, friends, I'm no Sal Khan. There's a shadow on your paper. But given I'm not in school today, I figured I'd go over this with you, kind of give you a couple of examples based on the videos that you already watched. So up at the top of the notes that you have, full kind of like list of things to consider. Just keep in mind that finding the area between two curves is essentially extending the idea of a Riemann sum. And remember, the Riemann sum is the sum of the areas of the rectangles as the number increases without bound. So the only difference now is the rectangles may be bounded not just by the curve in the x-axis, but between two curves. So we're still going to be adding together areas, except we have to figure out what our heights are based on the curves. So we'll start with dx integration, and the length of your rectangle is based on the distance from one part of the rectangle to the other, and so that's your top curve minus your bottom curve. And the width of your rectangle is a small change in x, so that tells us that we're doing dx integration, which means that our integrand needs to be entirely in terms of x. So for this function, I have three representative rectangles in here. The first one is over here. Really, things start adding up at this value of x and this value of x, and so in order to find those, we need to find the point of intersection, and we're going to solve this quadratic equation, in order to do that. So that is a, plus 2 minus 1, x is negative 2, x is positive 1. So those are going to create the bounds for our rectangle, or I'm sorry, our area. So I'm going to start from negative 2 to 1, and now I'm going to create the height of my rectangle, and the height is the quadratic minus the linear. So 2 minus x squared minus x, and the width is dx. From here, it's straight integration, so I'm not going to do that part with you. I'll leave that for you to evaluate. Second example, difference here. Notice that, again, these representative rectangles help us determine the height of our rectangle and which curves are going to bound. So here's our cubic. This is f of x right here, and this is g of x. And you can see around the origin that the top curve changes from f of x to g of x as we pass through this point of intersection. So again, knowing what our points of intersection are will help us set up our integral. So we have a 3x cubed, those zero out, minus 12x equal to 0, and we'll factor that. And so we see our bounds are going to be, here's our 0, our negative 2, and our positive 2. So we'll start with this area. So we'll start from negative 2 to 0, and the height of our rectangle is going to be f of x, 3x cubed minus x squared minus 10x minus g of x. You need those grouping symbols around your subtraction, right? Around that function we're subtracting. That's going to be important there. To that, we're going to add the area of this region, and so from 0 to 2, we're now bounded on the top by negative x squared plus 2x, and then we'll take away 3x cubed minus x squared minus 10x dx. And again, we will group our last function there. So that is the setup for the integral. You certainly would simplify, evaluate using the antiderivative, and go from there. So I'm going to flip over to the back. And this example is going to look similar to the second video that you watched on your flipped lesson. And we're going to look at this integral two ways. So I had mentioned on the other side that we look at the width of the rectangle, and that width of the rectangle here tells us that we're doing either dx, or in this case we're going to be introducing dy integration. So the region's bounded, and when you go on to do the next, the problems on the rest of this, you're going to use Desmos. to get that sketch for you. You don't have to know how to sketch these functions on your own. On your AP exam, you'll either have your calculator or you will have a sketch provided for you. So here's your sketch. This is the function g of y equal 3 minus y squared, also known as x equal 3 minus y squared. And this linear function here, x equal y plus 1. So if we're going to do dx integration, right, you see our vertical rectangles here. At this point, the curves change upper bound. So we need to figure out what our point of intersection is. I will tell you that this value right here is 3. So we're going to solve for our point of intersection. Bear with me. What is that? Plus y minus 2 equals 0. So y values at -2 and +1. So if y is -2, I'm going to pop that back up in here. If y is -2, x is -1. And if y is +1, x is +2. So that's this coordinate right here, 2, 1. And over here we're at -1, -2. So to set this up, we need to change these out of functions of y and into functions of x. So I'm going to come up here and solve for y. X minus 3 equal -y squared, so y squared equals 3 minus x. And y is both the positive and negative root of 3 minus x. The positive root of 3 minus x is this upper part of the curve, and then the bottom one here is the negative root 3 minus x. So I'm just going to add that in here. Y equal root 3 minus x, and down here y equal negative root 3 minus x. Linear function is easy. We start with x equal y plus 1, so y is going to be x minus 1, and that's this curve right here. So as we set up our integral, we're going to start with this region to the left of that dashed line, because in the entirety of the region, this rectangle is bounded on top by the linear function and on the bottom by the root function. So from -1 to 2, we have the top function, x minus 1, and we're taking away the bottom function, negative root 3 minus x. And to that, we'll add this region over here. So after we get from 2, we'll go from 2 to 3. The top bound is now the root of 3 minus x, and the bottom bound is now negative root 3 minus x, which could certainly be simplified if you were going to be doing some integration. That's 2 root 3 minus x dx. So certainly u substitution still holds as we do these areas, but I'm not going to have you evaluate this one right now. Let's go over to dy integration. So in dy integration, if you notice, this rectangle is now horizontal. And so the width of this rectangle, if you look at that width, that is a small change in y, and that tells us we're going to be doing dy integration. For dy integration, our bounds need to be y values, and our function needs to be written in terms of y. We already have that, right? Again, this is the point, -1, -2. Over here, we are at 3, 0. And up here, this is the point 2, 1. But what's nice about these horizontal rectangles versus the vertical rectangles is as I think of putting the rectangles entirely through this region, right? That's just one representative. I could put one here, I could put one here, I could put one all the way up here. It is always bounded on the right by the quadratic and always bounded on the left by the linear. So I don't need to write this area in terms of 2 integrals. I can keep it in terms of 1. Finding the length of your horizontal rectangle, you're always going to do right function minus left function. That's going to keep this length positive because these values of x are larger than these values of x, so that difference is always positive. So we'll set this up for dy integration. My lowest bound on y is -2. My upper bound on y is +1. The right-hand curve that's my g of y, is 3 minus y squared, and the left-hand curve is y plus 1. I would argue that this is a cleaner way to do area. The values you get out of both have to be identical, but I think method 1, because of that split, provides much more work. So as you go through the rest of this work, you're going to, on this page over here, you're going to go into Desmos and sketch the region bounded by the graphs of the algebraic functions. You're going to write an integral expression to represent the area. In some cases, right, this is 4 curves, so these are going to provide some bounds where you won't have to find points of intersection. But on the case of something like Part B, if you don't have the bounds, you need to find them on your own. So when you find those bounds, I want you to write the equation that you're solving to find those points of intersection and solve. These algebraically can be done without the use of a calculator. So again, Desmos to sketch the region. Once you have the region sketched, I want you to draw in a representative rectangle. Oh, I can't spell right now. And that rectangle is going to help you find the height of your Riemann rectangle. It's going to help you determine bounds, and it's going to help you determine maybe if dy integration is a better fit. So good luck, and definitely collaborate with people in the classroom. And I will see you on Monday.